All right, so we're back again. All right, let's get back to where we were. And so that would be chapter 3A. We were partially done with that, and then so we'll wrap that up, and then we will move on to 3B. And if there's time, we'll move on to 4. So we're going to start with quadratic functions, as you can see. And the reason why they're called quadratic is because we have a term with x squared in it. All right, so quadratic means at least one term in here has x squared in it. And this is the traditional form for writing a quadratic function, ax squared plus bx plus c. The only real constraints on these numbers is that a can't be 0, because otherwise it reduces to a linear equation. So other than that, any real numbers can be a, b, and c. Now, the one thing we have to watch out for with quadratic functions, of course, is that if under certain conditions, the solutions to a quadratic function will be imaginary numbers. Like say, for example, if you draw a picture of the parabola that this represents, let's say you end up with something like this. Under normal, let's say, all right, let's do 2 of them side by side so you can see them better. Under normal conditions, most of the time, you'll end up with something like this. You've got a parabola, which represents a quadratic function, and then it crosses the horizontal axis at 2 different points. And those are the 2 solutions. Actually, this is x1 0, because y here is equal to 0. So let's write it this way. And so these are the 2 solutions. They have different names. They're called the solutions. Sometimes they're called the roots. Or sometimes they're even called zeros because of the fact that this is where y equals 0. But what we do know is that these are real numbers. Okay, so you can see that since these 2 x's are on the real number line, the 2 solutions are in fact real numbers. But if the parabola never quite reaches the horizontal axis, as in a case like this, then we know that it still has 2 solutions, but they're going to be imaginary. Okay, and we saw, of course, a great deal of discussion about this in those videos we were watching last week. In this case, we have imaginary solutions. Here we have real solutions. But either way, we have 2 solutions. Okay, remember they mentioned in one of the videos that Gauss proved that for a quadratic function, you would have to have 2 solutions. In fact, his theorem said that the number of solutions of any polynomial functions equals the highest exponent in the function. Okay, so when we get to the cubic functions where we have a term, an x cubed term, we'll see that there have to be 3 solutions. But here, we're guaranteed to have 2 solutions, but we're not guaranteed that they're real. Okay, so with that being said, sometimes as far as terminology is concerned, this function is said to be of degree 2. All right, degree just refers to the highest exponent in that function. And sometimes you also hear it called a second order function because of, again, of the fact that it has a square term in it. So they both mean the same thing. The degree, the order, they represent the idea that there is a term with x squared in it, and that's the highest exponent in the function. Now, of course, we see a lot of these in practice. I mean, when you're, especially in a field like economics, you see quadratic functions all over the place. These express costs and profits and that type of thing. So they're very heavily used in practice because they show up all over the place. Some of the other functions that we'll be looking at, not so much, but this is a very commonly seen function in practical applications. Now, of course, parabola is the name of the graph that we were just looking at. I mean, basically, it looks like a big U. Any way to describe it, it looks like a big U. It is U-shaped, but also it's symmetrical. If you notice, if you were to draw a line down the middle somewhere, that just means that the right-hand side and the left-hand side are mirror images of each other. Okay, so you can imagine this is a big mirror here. The left and the right are identical to each other, which is why we say that the parabola is symmetrical. Okay. Now, we also can gain more information about the actual shape of this parabola from the coefficients in the quadratic function. For example, let's take a look at the next slide. You'll see that if this A term is positive, the parabola is said to open upward. In other words, it is just like a big U. And that's, of course, what we normally see. So that's the big U. So here's a simple example of that, which I did in Excel, of course, so it's not perfect. But if you want to get a better feel, I think we've already done this before, for what these graphs look like, you can switch over to this application called Symbolab, which does a really nice job with these graphs. Y equals 3x squared plus 2x plus 1. It should be able to give us a nice graph of this, and you can get a better feel. Yeah, see, that's, wow, look at this one. Interestingly enough, this one does seem to have imaginary roots. It does not actually touch. See, and it's harder to tell from this Excel graph. It looks like it actually touches the axis, but it really doesn't. But here you get a much better feel. Now, you notice that right about here where it reaches its minimum value, y is equal to 2/3. Okay, so that's why you can't really tell from this graph. It's too, let's say, crude, I guess. This one is a much better look at what we're actually seeing here. So it never quite touches the horizontal axis. And so therefore we say that this one will have imaginary roots. And you could prove it by plugging this in or using the quadratic formula, and you would discover very quickly that it only has imaginary roots. In fact, just as a little review, maybe we could do that right now. Why not? What the heck? You recall that the quadratic formula is x1 and x2 equal minus b plus and minus the square root of b squared minus 4ac all over 2a. And now where do these letters come from? That comes from the formula. Now here, assume that we're setting this equal to 0, because that's where the roots should be. And so in our case, since the function is y equals 3x squared plus 2x plus 1, that means that a is 3, b is 2, and c is 1. All right, and so let's plug those in and let's see what we come up with. So again, minus b plus and minus the square root of b squared minus 4ac all over 2a. And so a is 3, b is 2, c is 1. So when we plug these in, you'll have minus 2 plus and minus 2 squared. Hold on one second. 2 squared minus 4, 3 times 1. You can see what's going to happen here. Here we have 4 minus 12. And this is how you know, oh, here we go. We've got imaginary roots, because you can clearly see that we have the square root of a negative number. Now we can simplify this a little if you want to. This is actually the same thing as 4 times negative 2. So what you actually have here is -2 plus or -2 radical -2 over 6. And if you want to rewrite it in terms of I, you can see that this is just radical 2 times 2 radical 2I over 6. Because I factored out radical 2 from this radical. In other words, this is the same as radical 2 times radical 1. Okay, so anyway, this is our solution, and you can see that these are both imaginary roots. And it's all because the square root term is negative. Once we see that, we know obviously we must have imaginary roots. All right, now how about this other case? If A is negative, the parabola opens downward, we call it. And so we end up with something like this. Now, again, it's kind of not the best graph in the world. So why don't we do this? Let's go back to Symbolab. And all I did was change the first term to negative. And it does create through it. This one does have two real solutions, as you can see, although just barely. And again, this is a much better graph, obviously, than this one, where I don't know why it's so distorted like this. It's just not a good software package, I guess. No, I'm still looking into it. Maybe next time. Okay, so anyway, now again, I mentioned this earlier, we can't allow A to be 0 in this case just because we'll end up with simply a linear function, which is what we're obviously not trying to study here, but quadratic functions. Now, it turns out, though, that a parabola is actually much more interesting than we might have realized. Okay, we're going to now take a few minutes and more closely analyze the characteristics of a parabola. You'd be surprised how sophisticated this idea really is. A parabola actually has 4 different uniquely identifying characteristics. All right, we have the so-called vertex, the axis of symmetry, which of course simply means, remember that we saw that a parabola, whether it's facing up or down, is the same on either side. The axis tells us where this occurs. And of course, we also saw already that the solutions are the 2 points where it crosses the horizontal axis, if it does. And then we also have a y-intercept. And so those are the solutions. X1 and X2 are the solutions. Or again, sometimes they're called zeros because this is where the function equals 0 and the y-intercept would be here. All right, now, so let's see. What we need to be able to do is identify where all of these take place to uniquely characterize our parabola. All right, so how does this work? Well, first of all, what does the word vertex mean? This is a mysterious word. Maybe we're not sure what that means. Well, in this context, it means, depending on whether it's upwards or facing up or down, that point is either the maximum or the minimum. So, for example, if A is positive, the parabola opens upward. Let's say we have something like this. Actually, let me draw that again. So the vertex is this point right here. Let's say this is the point, I don't know, 3, -2. For this parabola, because it's facing upward, this would be its vertex. This is simply the minimum. And in fact, the slope of the function at that point is equal to 0. So what that means then is that you could find this point, you can find the vertex by taking the first derivative, which we haven't explained yet, but we will. The first derivative is another name for the slope of this tangent line. This comes up in a later chapter, but I just want to mention it right now. The first derivative, slope, i.e. slope of the tangent line, and setting it equal to 0. Now here, instead of doing that, because we haven't started doing derivatives yet, we actually have a formula that lets us do this instead. All right, so in other words, yes, that's true. We can take this approach. We can find the equation of a tangent line and set it equal to 0. But as it turns out, there's also a formula that we can use. Now, of course, if it's upside down, if the parabola is upside down because the squared term is negative, then the vertex would be the maximum point. In other words, imagine this being flipped upside down. All right, so you can imagine what that would look like. Something like this. Again, you'd have a tangent line with a slope of 0. And by the way, if you've forgotten, tangent simply means it only touches the function at one point. This must be the vertex because the function cannot be any larger than this. So let's say this is the point 3, 7. This is the vertex. And all it means is the maximum point on that function. In case of geometry of the curve, it's the top. It's like, think of it as the top of the mountain, I guess. So that's what that word actually means in this context. Vertex can mean other things as well. In fact, why don't we take a look and see what are some of the other possibilities here, just in terms of pure English. Let's, no, now we're coming up with proper names. I thought, no, there's a dictionary online, isn't there? I think so. I don't want the word of the day. I don't want to know what pleonasm is, although I guess we should learn every word we can. But let's look for vertex just to see what they come up with. Okay, oh, it does say, all right, one of the top definitions is the highest point of something, the apex, summit, top, the vertex of a mountain. How do you like that? Well, now we know where this word comes from. Now, like I said, every word, just about every English word has many different meanings, many of them of which have absolutely nothing to do with each other. But look at this, the point in a geometrical solid common to 3 or more sides. Wow, how do you like that? The intersection of 2 sides of a plane is the vertex. How do you not like that? So anyway, the word vertex here, we're thinking about the highest point, although unlike with a mountain, which has to be facing up, a parabola, it has to have a peak like this. A parabola can also face the other direction, so it can be either the minimum or the maximum. Okay, so either way, that would be the vertex. Now, as I said, there is a formula that will enable us to do this based on, remember, our definition of a quadratic function as f of x equals ax squared plus bx plus c. So this is a point. It's written this way for a specific reason. H and k just represent the coordinates of the vertex. In other words, this is the x coordinate, and this is the y coordinate. The reason why they're using separate letters is to avoid confusing them with x and y. All right, so let's just take a look at a quick example of this. And you'll say, oh, that wasn't so bad. All right, so a times h minus h squared, x minus h squared plus. All right, well, I guess we have to look at the weather. All right, enough of that. All right, let's get back to this. So here we go. Now remember, what we're looking for is this. Ax minus h squared plus k. How does this turn into this? Okay, now remember again, based on our standard definition of a quadratic equation, this implies that a is 2, b is -6, and c is 7. So how do we go from one to the other? And here's a picture of it, which, by the way, as usual, let's take a look at Symbolab to get a better feel for what it really looks like. Think of this as a first approximation. It's very hard to judge where it actually touches the axis. You can see why, because of the way these numbers are so large, that this appears to be touching when in fact it starts at 7. So let's try it over here. So as much as I love Excel, it's really not the best tool for this job. 2x squared minus 6x plus 7. All right, let's see what this thing looks like. And then you might be able to identify just by looking at it what the vertex is. Now, the other thing about Symbolab is it actually will often identify some of the points that we're looking for on the graph. And so, as you can see, it's having an issue. Man, that was scary. I wonder if it was a complicated function. All right, so you can plainly see now. We're gonna cheat a little bit here. The point 3 halves comma 5 halves is actually our vertex. All right, but so we know that in advance. We're going to prove it now. Okay, so here's the form. Now, because actually, let me copy these. So there's another formula here. So there's two formulas actually going on here. F of x is ax minus h squared plus k. H itself has its own formula. And so in this case, it's minus 6 minus 6 over 2 times 2, which is 6/4 or 3 halves. Now, all right, you see, we already figured that one out from the Symbolab. So we already know from Symbolab that k is 5 halves, but where does that come from? All right, well, let's see. Now we have this information. We can actually plug 3 halves in here and reason it out algebraically. Okay, so how would that work? Okay, you ready? Let's check it out. So again, given that h was determined to be, from that formula, 3 halves, the way this works is that k is the value of the function evaluated at h. Okay, so in other words, the original function was f of x equals 2x squared. Oh, there it is. It's right here. Okay. So f of x is 2x squared minus 6x plus 7. And so when you replace all those x's with 3 halves, algebraically, we discover that k is 5 halves, which we've already seen in Symbolab. Yes, go ahead.
Sorry, I guess I didn't follow closely enough to understand where 3 halves and 5 halves came from exactly.
Okay, here we go. So the first one, the h comes from this formula, which is taken from the original quadratic equation. So remember, the quadratic equation is ax squared plus bx plus c. And because our equation was f of x equals 2x squared minus 6x plus 7, that implies that b is b over 2a, negative b over 2a. And so b is negative 6 from here. And then here we have a, which is 2 from here. So you plug those in and you've got your h. Okay. And then that number goes into this function and replaces the x. Okay, so the second step is to say, oh, all right, well, why don't we do this now? Here's the function.
H symbolizes the same placeholder as x in the function?
Does, yes, that's exactly right. And so therefore, whatever this equals is our k. So again, it's a two-step process. It's actually less painful than it looks, because all you have to do is use this relatively simple formula for h, and whatever that number is, plug it into your original equation, and that will give you your k. All right. And so, yes, as we've already seen, and we knew that already.
So like in other words, h is x1, and plugging the x1 in gives us our x2.
Well, actually, no. H comma k is the equivalent of x comma y.
Okay.
Remember, they changed the letters because otherwise you'd be confused about which x is which and which y is which. This is a specific set of points. This is one specific point, but the first point is an x and the second is a y. So in other words, this point would be like here, for example, x would be 3/2, comma, and y is 5/2. So in other words, think of the h as an x and the k is a y. H is some independent variable. In this case, it's 3/2, and then y is the corresponding value of the function at that point.
That makes more sense.
Okay, good.
Thank you.
You're welcome. So then here it is. Now, what does this have to do with our original expression, though? Remember, way back we said this is how we express the function. It turns out if you plug these numbers in, see, now it's hard to believe, but this is actually the same thing as 2x squared minus 6x plus 7. If you fill it out, if you take this and expand it and do all the work, you'll see that these are the same thing. What's different is that here, when you look at it, you can see right away, this is h and this is k. So imagine yourself taking your original quadratic equation and rewriting it in a form where it's easier to see what is the vertex just by glancing at this thing. So you don't have to do this, but it's just, you should be aware that there is an alternative way of writing out this equation so that the minute you spot this, you can see right away the identity of h and k. But for our purposes, the only thing we really needed to do is oh yeah, go ahead.
So you were saying that so in f of x equals the one above f of x equals 2x squared, that do h and k tell you the location of the vertex?
Yes, they do. Yes, they do. Exactly.
Okay, that makes sense.
Yes. So now, in other words, it's just like, imagine that you need to know this vertex for some reason. This form will show it to you immediately. By looking at it, you can see that, oh, h must be 3/2 and k must be 5/2. You do run into this sometimes where you've got alternative ways of expressing the same equation, and sometimes one version is more convenient than the other. And so if for some reason we need to know the vertex, we might want to write the equation this way instead of the original form right here. But I mean, the actual, if you have this original quadratic equation, remember, h is just negative b over 2a, and k is f of h. This is all you really need to remember. Okay, and with this I mean take the original function and replace all the x's with h's. Whatever h happens to be, which is a constant. All right. So now, how about the symmetry business? Now, if that's the vertex, now, based on the way a parabola is shaped, it has a very nice regular shape. Okay, there's really only two things that can happen. It can be a big U, or it can be an upside down U. That's pretty much the extent of it. So it stands to reason wherever the vertex is, remember, this is where the tangent line is flat. It stands to reason that the axis of symmetry, which is just a vertical line, which separates the two halves, would cut through the vertex. Now, if they were drawn properly, you could see that the left-hand side here is a mirror image of what's going on the right. Well, actually, I shouldn't color in these parts. Hold on. This piece on the left is a mirror image of this piece on the right. And the dividing line is this thing. And we'll call this, make it a little thicker there, the axis of symmetry. It sounds very impressive, doesn't it? The axis of symmetry, that could actually be the name of a band, don't you think? How cool would that be if you had a band and you call it Axis of Symmetry? What kind of music would that band play, do you think? If you saw that advertised, hey, Axis of Symmetry is opening tonight for Metallica, what would you expect them to be playing?
You gotta spell axis like the weapon instead.
Yeah. Oh, that would. Yeah, Axis. Yeah. That would work for math rock. Yes, we have to create a new form of music called math rock.
Oh, that actually exists.
Does it really?
Yeah, it's really good. It's like I think it's like it has like these jazz syncopations within it. I think it's really cool. You should listen to it.
I did not know that.
It's beautiful.
Math rock is a category of music, but it's also like super vague because it's just defined by like complex time signatures.
Yeah.
So you could have math rock that sounds like heavy metal with like complex time signatures, or you could have like indie math rock and have it be like super laid back.
I did not know any of this.
Look up the
So-
band called Chan. Some really nice math rock. Chon, Chon.
Without this, okay. Yeah, math is metal, isn't it? Yeah. All right, I will investigate this because I'd like to hear what this sounds like. I figure somebody would have come up with this idea sooner or later. No, I like this. This is very interesting. And so I guess does that mean you guys are just music fans, or are you musicians?
I think I'm both. I'm starting to learn the acoustic guitar, and I love listening to different genres of music. Also, on the topic of math rock, you could also listen to this band called Covet, Covet.
Love it. Oh, right. Like being jealous of something.
Yeah.
Oh, wow. Man, there's so much. It's all coming out of the woodwork now. Yeah, but you're right. Even a lot of classical music could probably be defined that way. Interesting. Wow. Who knew? In fact, you could probably have a whole class about this. Got it. If there's one school
Definitely.
that can have a class like this, it's Purchase. In fact, maybe they do have a class like that if you look in their catalog. Yes, math is everywhere. In fact, that's the thing. The great thing about math, you can run, but you can't hide. It is everywhere. That's right. That's why the sooner you learn how to deal with it, I mean, the more you know about it, the more you'll be able to deal with it when it shows up at your doorstep. All right. Anyway, so very simply then, if the axis of symmetry coincides with the vertex, well, then the formula for this is so simple. Watch this. This is just, now, if you notice a vertical line means that X is a constant. So that's exactly how this works. So whatever the, the vertex is, We set x equal to that, and there's your axis of symmetry. So x just equals this h that you just found earlier. And so that's all that this is. All right, so when you identify this is your h comma k, and just let x equal the h, which means that it's a vertical line. Like for example, this is the line x equals 2. It's not actually a function. It is actually simply a vertical line, but this is how we'll express the axis of symmetry.
So just to be clear, the axis of symmetry could also be written as h equals.
You could, because h is defined as negative b over 2a, you can just write that the axis of symmetry is x equals h.
That makes sense.
Okay, now I got 2 questions. Who
I have a
wants to-
question. Yeah, so how would you want us to rate the axis of symmetry whenever we're doing it?
Well, what you would be doing is trying to figure out the exact value. In other words, before, remember we saw that it was 3 halves.
Yes.
So then in this case, x equals 3 halves is the axis of symmetry.
No, so you would want us to leave it as a fraction?
Oh, yes. No, actually, yes. You probably should. I mean, you could write 1.52 if you want to. It doesn't matter.
Yeah.
But I don't know. It just seems a little
Bizarre.
that sometimes it can go either way. You know, the thing about math is there's certain conventions, I guess we'll say, that are not really rules because they're just sort of a matter of judgment. But here's an example of what I mean. Like if you came up with a solution like this to some problem, brother, x equals 6/3, you probably wouldn't just leave it like that. Most
Just
likely,
two,
you would
yeah.
say, yeah. Or if you have something like this, this is another one you run into sometimes. 1 over radical 2, let's say. For some reason, mathematicians don't like to have irrational numbers in the denominator. So what they would have you do is multiply it out by radical 2 over radical 2, so that at least you have a rational number in the denominator. And again, it's not that there's anything wrong with this, but the convention is just to try to avoid having radicals in the denominator like that. Or if you have an equation like this, by convention, what you would do is you would rewrite it as you want the highest order terms first, and you work your way down to the lower order terms. There's nothing wrong with this expression, but this is the one that mathematicians prefer. So these are all conventions. They're not like hard rules, because it's almost like, why do we have the fork on the left and the spoon on the right? I mean, when you stop and think about it, there's no real reason for that. It's not like the laws of physics are involved or anything. It's just that this is how humanity has always done it. You know what I mean? It's the same idea.
Okay. Thank you for clarifying.
You know, I mean, it's possible. I shouldn't say that. It's possible that there was a point in history where there's a very specific reason for doing this, but I don't think that's the case. But these are like just conventions.
Okay.
And if you put down, like if you write down on a test this, you're not wrong. It's just that this is preferred.
Okay. Thank you for clarifying, Professor.
Sure.
I very much appreciate it.
Okay, sure. And of course, this silverware thing can get really ridiculous. If you've ever been to one of these historical mansions that crazy rich people lived in, you'll see the table settings, and there could literally be a dozen pieces of silverware sitting there, and you were supposed to know what to do with each one if you were showing up at one of these events. So anyway, that's what made me think of it. It's like a set of rules that you're just supposed to be aware of. So anyway, eating, if you had these two to the left and right, you can still eat. It's just that people would have stared at you, I guess. But anyway, so yes, so that's all it is. So you've got your vertex, and then the axis of symmetry coincides with the H. Or even, and if it's upside down, same thing. This is still H comma K, and this is your axis of symmetry. All right. So for this one, of course, I think it's pretty clear that the axis of symmetry is 3 halves, because that's where we found our vertex. it was 3/2, comma 5/2. And that would be our axis. And you can tell just by looking at it, the left-hand side and the right-hand side are mirror images of each other. Now, if you go to Symbolab, sometimes they present all this stuff for you. Let's go check this out for a second. Even without being asked for it. See, it even says it right there. The vertex, they're giving you the entire point. You don't actually need, they're basically saying the vertex coincides with this minimum point. So therefore, that means 3/2 must be your axis of symmetry. And then here, you notice how they're also giving us the y-intercepts. They're telling us where this function crosses the vertical axis, which we do want to know. Okay. Now this we already remember, we just did it a few minutes ago. Here is our quadratic formula, which you learned somewhere in your travels throughout math world. And this is one of those functions that for whatever reason, people rarely forget. There's something about it that makes it stick in your memory. Maybe the teacher made you learn it, like really pushed it hard, but it's been my experience that very few people actually have forgotten this formula, no matter how long it's been since you learned it. So anyway, here's a fun side fact though. If you were to use this quadratic formula, and again, this is because of the way the parabolas are shaped. If you can imagine that here's your parabola. Oh, actually, let me do this a little better. I'll just keep it simple. Let's say this is 2, 0 and 4, 0. This is your vertex. And let's say it's 3, -4. Well, the axis of symmetry, by definition, is just halfway between these two solutions. And so that means that if you know the two solutions, the axis of symmetry equals the average of the two solutions, as long as they're real. If they're imaginary, then this is not going to work out, but the average of the two solutions. So if you did the solutions first, you wouldn't have to bother with the formula. You would already know what the axis of symmetry is by averaging them out, the axis that is. Okay, so this is the line x equals 3. This is my axis of symmetry. And I know that because it's the average of 2 and 4. Okay, these are my two solutions. Okay. That's because the parabola itself is symmetrical. It's the way it's shaped. We know that it's not going to go through these weird pieces like that, let's say. It's just a nice big smooth curve. Yes, go ahead. All right, whoever's first, go ahead. Oh no, what did I do? Did I knock somebody out here?
Oh, I don't think so.
Oh, I thought I accidentally deleted somebody from the list. All right, whoever, go ahead. Whoever's next, go ahead.
Can you reiterate what you had said, because it felt like you were going just a bit too fast? And
oh, okay. Which part do you want?
So how did you describe the axis of symmetry being? Did you say that it was easier when using the quadratic formula?
Well, what I'm saying is that in order to find the axis of symmetry, if you're going to find the solutions anyway, you don't need to separately calculate the axis of symmetry, because it is simply the average of the two solutions. Okay.
Okay.
All right, this is an example. I just made this one up on the spot, but we can do it with this case as well if you want to. In other words, the axis of symmetry is actually the average of these two solutions. In addition to the formula that we saw, Well, that formula, by the way, was taken from the quadratic formula. So this is why it's not a coincidence. I don't know how awkward it would be to prove it, but what we could do instead is go back to our original formula. Now, I think we're going to do this anyway. Oh, why? Yes, we are. No, wait. It looks like that's a different example. Let's try. Oh, no, you know what? I just realized this one has imaginary roots. So we can't use this as our example, but there's a good example coming up. So let's try this one and we'll see how it works. So we start out with a very nice, simple quadratic equation, x squared minus 3x minus 4 equals 0. And of course, now don't forget, this one has a coefficient of 1. There's an implied 1 here. All right, so that way in this quadratic formula, this is actually a 1. So a is 1, and of course then b is -3, and c is -4. So then I can plug those into my quadratic formula, and I can find my two solutions. It looks like they're going to be 4 and 1. Why don't we, I'll tell you what though, let's go take a look at this picture in Symbol Lab before we do anything. And that way we'll have a better feel for where we're going with this. X squared minus 3x minus 4. Nice, even look, I mean, you'll see it's a very nice graph. And it crosses here. Oh my God, what happened? Is that what we... I don't know. That's, hold on one second. X squared minus 3x minus 4. It looks kind of weird. Well, something strange. It usually gives us the intercepts. I don't know what's going on here. Well, you know what it is doing? It's helping us, it's showing us the vertex, which is okay, but wow, I was expecting it to show me the intercepts, and for some reason it's not doing that. So, all right, well, anyway, let's do this the normal way. Let's use the quadratic formula, and we'll plug in these numbers. And so let me just up here somewhere put these numbers down again so you can see them. We have x squared minus 3x minus 4 equals 0, which means that a is 1, b is -3, c is -4. Okay, so you've got, actually, you know what, let's do this. I like to have everything together on one slide whenever possible. I think we can just about do it here. Hold on 1 minute. There we go. Just so you can follow along and say, oh yeah, I see what you did. So in other words, this is B. This is B. We have 4AC all over 2A. And then you can see algebraically under the square root sign, we have 9 plus 16. Over here, we have plus 3. We got to watch it with those negatives. And then we divide everything by 2. And so I have positive 3 plus or minus the square root of 25 over 2. And of course, 25 is one of our favorite numbers because 25 is what we call a perfect square. And the square root of that is, of course, 5. And so we've got 3 minus 5 over 2, comma, 3 plus 5 over 2. And so that reduces to -1 and positive 4. So let's try to draw the graph real fast. So that's going to look something like this. -1, 0, and 4, 0. Now, here's the thing that we're looking for if we're looking for the vertex and the axis of symmetry, the formula for H, remember, was minus B over 2A. And in this case, B was -3 and A was 1. Okay, so that means this is 3/2. And then K would be f of H, and the original function was x squared. So we'll have, hold on one second. F of x is x squared minus 3x minus 4. So therefore, f of H would be 3/2 squared minus 3 times 3/2 minus 4. Okay, so we can convert these all into fourths. I'll do that up here somewhere. We'll have 9/4 minus 18/4 minus 16/4 is, let's see, what is that? Minus 25/4. But the point of all this is that this 3/2 is also the axis of symmetry. And if you notice, it is simply the average of -1 and 4. So if you put together 4 plus -1 over 2 is 3/2. Okay, so in other words, all we're saying here is that if you've already calculated the solutions, you don't really need to separately calculate the axis of symmetry, because you know that it is the average of these 2 points, -1 and 4, because those are our 2 solutions, and it has to be halfway in between them. All right, so that's what that was all about. Now, quadratic equation. Oh, this is another example. So this time we've got x squared minus 6x plus 8. So this time A is 1, B is -6, C is 8. So we plug in these numbers as we always do. All right, let me just move this to the next page so you can see what's going on. And I'll just quickly remind you that A is 1, B is -6, and C is 8. So you just go ahead and start plugging in the numbers, and as long as you're careful, you'll get to the correct solution. And once again, we got lucky over here. We got a perfect square. So you can see that this reduces very nicely to a couple of integers, 2 and 4. And so what we can do now, in fact, why don't we go visit Symbolab again, and you can visually see what this is supposed to look like. X squared minus 6x plus 8 And so it crosses twice. Now see, this time it gave me the intercepts for some reason, 2 and 4. Well, we already have proved that. But the axis of symmetry, which normally we would use a formula for, you can see it's got to be 3. It's halfway between those two numbers. But let's prove it. Okay, if we use the formula, remembering that A is 1, B is -6, C is 8, H is -B over 2A, which we predict will be 3, minus -6 over 2 times 1, 6 halves, and in fact it is 3. Okay, so the axis of symmetry is right here. And then the vertex is 3, comma. If we want the full point, we have to go back to the original function, which was x squared minus 6x plus 8. F of 3 would be 9 minus 18 plus 8, which is -1. Okay, so H is 3, K is -1. All right. All right, so now we're going to come up with an interesting little application of this, which might come as a surprise to you, but let's take a look at this problem where we've got ourselves confronted with a situation where we're building, believe it or not, a picnic table, and we have to figure out the proper dimensions. And surprisingly enough, this will end up involving the quadratic formula. All right, so let's check this out. All right, when you're done, I'll just give you a minute to finish, and then we'll move on to this interesting example. Okay, so let's say that we're building a rectangular picnic table. And we're told there's 2 requirements. Somebody's got a deck in their back, and they've got just enough room. And we need 2 pieces of information. First of all, the length is 2 feet more than the width. And so let's say that x will be the width, and the length could be x plus 2. We could do it the other way around. This could be x, and this is x minus 2. It doesn't really matter. But we also know that the area has to be 35 square feet. So you might recall that the area of a rectangle is the length times the width, of course. Nobody forgot that, did they? No. So you're going to have x plus 2 times x, which is x squared plus 2x, and we're told that this must be equal to 35 square feet. So we know that x squared plus 2x is 35. Now that's almost, but not exactly in the proper form for a quadratic equation. So all we have to do is subtract that 35 from both sides, and all of a sudden, look what we have. A quadratic equation. And guess how we're going to solve that? With the quadratic formula, where A is 1, B is 2, C is -35. And it's not that hard, is it? No. There's just one wrinkle that we'll run into. What is that wrinkle? All right, let's find out what the wrinkle is. Let's plug everything in here. Okay, so remember our equation was x squared plus 2x minus 35 equals 0, which implies that a is 1, b is 2, c is negative 35. All right, so I'm going to plug these in. All right, let me first copy this formula so you can see everything together in one place. And again, remember that a is 1. B is 2, and C is negative 35. All right, so we start plugging in our numbers in and move along here. And we discover, ooh, we're very happy over here because the value underneath the square root sign is itself a perfect square. 144 is a perfect square. And all that means is that its square root is an integer. So its square root is an integer. And so we end up with a couple of integers for our solutions, -7 and 5. And remember, this is a parabola. So there's a very strong chance it'll cross the x-axis with a negative value. There's just one problem, though. What is that problem? Now -7 is a perfectly valid solution to this equation, but we're dealing here with physical dimensions. And so what that means is you've got one solution that can't possibly work in the real world because there's no such thing as -7 inches or feet. So that just tells us that we must go with 5 as our solution. All right, so in other words, if you drew this thing out, you would see, let's just draw this real fast. This is your parabola. You've got -7, 0 as your, and positive 5, 0 as your solutions. But because we're dealing with physical dimensions, that means only the first quadrant is relevant in this case. So in other words, you could almost say that we need to solve f of x equals x squared plus 2x minus 35 over the interval from 0 to infinity, meaning that we're going to disregard anything in the negative, the left-hand side. And also, of course, we only want positive y's. So this is the range of possibilities. So we must pick this as our solution. So the solution is that x equals 5. Now, if you recall, we defined x to be the width. Our length is x plus 2, which is 7. So the dimensions of our table are, in fact, 7 by 5, which is 35 square feet. And that's what we wanted. The length is 2 feet greater than the width, and the area is, in fact, 35 square feet. So that must be what we need to do to build this table. All right, so does everyone see that? So this happens sometimes in practice. If you're dealing with real numbers like are real items like feet or inches or dollars or percentages or whatever, as long as we cannot have negative values, then all we have to do is restrict the solution to a certain interval, and then we'll end up with what we need. Okay, so we can't clearly pick -7 square feet or -7 feet, but 5 certainly does the job. All right, now there's one more component of this parabola that we needed to identify. The fourth and final component is what we're going to call the y-intercept. And all that means is, where does this function cross the vertical axis? Okay, so for example, let's say this is our parabola. This is what we're looking for. This is the point where x is 0, and this is some value of y, which forces the function to equals, for x to equal 0. So how do we solve for something like this? Well, if we know that f of x equals ax squared plus bx plus c, I need to find the value where x equals 0. So watch what I can do. I can evaluate this function where x equals 0, and I'll get my answer. So the c is my vertical intercept, or y-intercept. All right, so for this last equation, for example, remember we discovered this is y equals x squared plus 2x minus 35. Oh, you know what we forgot to do? I think we forgot to plot this on Symbolab. Hold on one second. Let's go over there for a second and look at it. Yeah, we never did this one. So let's take a peek. X squared plus 2x minus 35. Let's see what that actually looks like. Yeah, there it is. And so you can, what are we looking for here? Wow, this is kind of weird. But anyway, right about here, see, I don't know what they're doing here. But the point where it crosses, you can kind of see, is minus 35, although it's hard to tell here. Sometimes the labeling of these graphs is kind of bizarre, but it should be right about here. That's where it's crossing on the vertical axis. So this last term, the c, uniquely characterizes the vertical intercept. So that one is easy to find. I mean, really easy. So when you stop and think about it, as long as you remember how to use the quadratic formula, finding these 4 components of a parabola is pretty straightforward because of how they're all ultimately related either to the equation itself or the solutions. Let's see, let's go back again. So remember, the vertex is the maximum or the minimum, and that's our point h comma k. Oh, yes, go ahead.
Apologies for the interruption, Professor. But I was wondering if you could go back to the y-intercept slide whenever you're done explaining this.
Yes. Let's go. I'll do that right now, and then we'll come back.
Oh, okay.
I'm just gonna. That's just for wrapping up purposes.
Oh, okay.
All right. Yeah. So no, let's get this out of the way first, and then we'll. I just wanted to summarize, basically.
Oh, okay. I apologize.
Yeah, that's it. That's it. That's all you have to know right there. So in other words, because all we're looking for is the point where x equals 0, then literally all you have to do is replace all those x's with zeros, and whatever you come up with is your y-intercept.
That's easy enough.
It is. I know. Isn't that nice when it's easy like that? All right, so yeah, so I was just going to say all of these actually are very closely related to each other because the vertex, now remember the vertex has that formula, but if you're going to solve for this thing anyway, if you do have the solutions, the H is also the average of the solutions. And then the axis of symmetry is just x equals h. And then the y-intercept is just the value of the function where x equals 0. So as long as you can do this part with the quadratic formula, the rest really just sort of falls right into place. So although it looks very formal and scary, this really is not very complicated at all. That's one of the nice things about parabolas. They're so straightforward. They're so nicely behaved. Unlike, let's say, arctangents or something ridiculous like that. So this is, yeah, it's kind of, I mean, nice to break this down and analyze all the components of a parabola because, you know, you don't always think about all these details. But every function in math has some specific defining characteristics that we need to be aware of. All right, now what I also have down here is just a brief discussion about finding the domain and range of one of these functions. For example, for a quadratic function, the domain is all real numbers. Okay, so in other words, no matter how you draw a parabola, what you're going to have is, I mean, eventually the curve, it goes up forever. Okay, so in other words, and it may look like if here we just stop drawing it, but this actually goes up to, this goes up forever, this goes up forever. So that means that every number on this real number line is going to be eventually reached by this parabola. So the domain is the entire real number line, which will express as negative infinity up to positive infinity. In fact, you know what we could do? Let's go back to our old friend Symbolab. Sometimes it produces this information and sometimes it doesn't. I'm beginning to see that it needs a little bit more analysis before we, I'm still learning the thing, let's put it that way. So no matter which one we pick, let's go back there real fast. I'm wondering if it did. Yeah, it's kind of strange how sometimes it gives you exactly what you're looking for and sometimes it doesn't. Let's try a different one. Let's try a really basic one and see if that helps. So that's a nice, well-behaved parabola. Well, I was wondering if it was going to give us, well, it figured out the vertex for us. And here's the axis of symmetry. The y-intercept is right here at 0, 1. There's the only solution. There's actually, there is a solution. This vertex actually is the solution because it's the only point where it touches the the horizontal axis. But I was wondering if it was going to give us the domain and the range. Oh, here it is. The domain is all the real numbers. Oh, that's good. All right. Now, the range is a little trickier because it depends on the sign. Yeah, see, it's got both of them, the vertical and horizontal intercepts. It's got all this other stuff too. We're not going to touch any of these topics, like the focus, the directrix, you know, I mean, there's all kinds of bizarre ideas associated with this function, which we'll not be doing here, that's for sure. Inflection points, you'll run into that if you get into Calculus 1. Global extreme points, yes, you'll be analyzing that too, but not here. But anyway, let's go back and look at how this works for calculating the range. The range depends on the sign of A, okay? And if you notice, this should look very familiar. This is H. Okay, so in other words, if A is positive, the range of this function, which means the values of Y, is the interval from f of H up to infinity. And all that means is that, remember, this is your H right here. It means that Y can't go below this point. Oh, and one more thing while we're at it, I just realized, why not just write it like this? This is just K. Because remember we said earlier, K is nothing but f of H. So this could actually be rewritten. F of H is K. So that actually might be an easier way to express it. And I think by doing it that way, it's easier to see why. Okay, K here is as low as it goes. So the range in this case is everything from K up to positive infinity. Man, this is pretty deep stuff, isn't it? Yes, it is. It's very deep. Now, if A is negative, now remember, that's the case where the parabola slopes, faces down. Then we have the opposite case. And then all that means is that Y is restricted to being somewhere between K and negative infinity. And that's what this means. In fact, this could be rewritten as -8 infinity comma f of H, or negative infinity comma K. All right, let's look at another example. And before we do that, let's go graph it on Symbolab. Okay, as long as it's there, we may as well put it to good use. Minus 5x squared minus 5x squared plus 9x minus 1. All right, let's take a look at that. All right, well, there you go. Now you can see that the vertex, oh, it's kind of interesting, 9/10 comma 61 over 20. Wow. That's not a pretty pair of numbers, is it? H is, and we could have figured this out for ourselves. I mean, really, it's minus b over 2a minus 9 over 2 times minus 5 minus 9 over minus 10. That's H. And then K would be, oh my God, all right. Oh, what the heck, let's try it. K would be f of 9/10, which is minus 5 times 9/10 squared, plus 9 times 9/10, minus 1, minus 5 times 81 over 100 plus 81 over 10 minus 1. This is minus 405 hundredths. And then we can convert all these to 100ths. Let's move this over here somewhere. Minus 405 over 100 plus 810 100ths minus 100 over 100. That equals, let's see, A10 minus 405. 305 over 100. And then I guess we can simplify that a little further. Let's see. 61 over 20 I have. Yeah, okay. So that, okay, with all that being said, so the vertex is 9/10, comma, 61 over 20. And again, you can see the picture for yourself right here. But we're looking for this point, 0, comma, wait, sorry, no, we're not. Sorry, we're looking for the domain and the range. We know that we don't have to worry about the domain. The domain is just automatically the entire real number line. It's the range that we're looking for, which means everything from 61/21 down to negative infinity. Okay, so in other words, if you drew this thing, all right, trying to match it up a little bit here. All right, here's our vertex. All right, hold on one second. That's our y-intercept. But what we're interested in is the range. And that range means everything from y cannot go beyond 61 over 20. So the range is minus infinity up to 61 over 20. It can include 61/20, so I'll put that square bracket here. But how do we, what we could have done to make things a little quicker is if you go back to the original equation, A is negative, which means this is downward sloping. And so the range, according to our formula, is and so we've already done all the work here. So we already know that this would be f of 9/10. And that would just end up being negative infinity up to 61 over 20, including 61/20. Okay, and in fact, the formula here does indicate that this bracket means it includes this number and then everything down to negative infinity. Ooh, that was a lot. So we are now experts on parabolas, aren't we? And quadratic functions for that matter. Yes, we are. This is our thing now. So that's good because you're gonna need this. If you run into any class that has math involved in it, in any other discipline, sooner or later you're going to run into quadratic equations. Okay, they're everywhere. All right, so now what comes next? Does it make you shudder to think what must come next? It isn't necessarily the case that each topic is more difficult than the last one, although it may work out that way sometimes. They're just different topics. All right, well, okay, some of them are more complicated than others, but like in chapter 4, we're going to be doing some really interesting functions which involve natural logs, which you may not have thought about for a while. But right now, we've got some more things to do. We're going to introduce the concept of the polynomial, which is basically polynomial. If you look at the origins of the word, it just means many numbers. And so a quadratic equation is a specific case of a polynomial. So let's see, now this is in general what a polynomial looks like. Okay, so this is the most general possible form of a polynomial, of which both a quadratic function and a linear function are just special cases. So yeah, you can see it looks very complicated because we're trying to express a very general idea. This applies to every polynomial out there. And you notice the 3 dots, which means that it keeps going down until we reach these last 3 terms. This last one is just simply a constant. So it looks scary, but it just means that you've got the a's are the coefficients, and oh, good. Okay, so yes, this is a polynomial, and oh yeah. So, but you might recall now, if all we have, this piece here is a linear function, if you add to it this second term, it becomes a quadratic function. And then if you keep going to the left further, you can include, for example, cubic functions. So as you keep going to the left and adding more terms, you're moving up into the higher order terms. And again, there it is, many numbers. Poly is many. It might be Greek. A lot of math words come from Greek rather than Latin. In fact, why don't we do this? Because we can, just because we can. It joins 2 diverse roots, the Greek poly meaning many and the O, and it comes with Latin. Oh, it means name. It's often used to represent numbers. Nomial. Yeah, I guess I can see that. Nomial could be better described as name. Look at this, though. The ancient Greeks didn't think of this word. It was first used in the 17th century. Some genius came along and said, why don't we call them polynomials? Prior to that, people had been using the word Latin. A binomial, bi is the Latin for 2, of course. How do you like that? Man. Who would have thought that these words would be so interesting? But they are. All right, well, anyway, so these are the special cases. A linear function means, and we call that degree 1. Okay, so in other words, that would be f of x simply equals, based on the formula on the previous slide, I'll keep using this notation. But I mean, you recognize that this could be written as mx plus b. The second one, the quadratic, is based on the notation in the previous slide. And of course, what you could do is simply rewrite this as ax squared plus bx plus c, which is what we frequently have done. But of course, it means the same thing. And then the cubic equation is has a term with x cubed in it. And then you can replace it with any. There isn't a standard set of letters here like there is for the linear and the quadratic equations or functions. You can just leave it like this. This is cubic, and cubic functions, end up looking often like this, although not always. They potentially can cross the axis 3 times. Well, now, let's see. So in the next slide, we're going to have a quiz to see which of the following qualify as polynomials. The one thing we forgot to mention here is that there aren't any negative exponents. It's understood that these are all positive. In other words, n is the largest number in this group. So therefore, none of these can be negative. So therefore, which of the following are polynomials? Well, the only one that doesn't count is this one. This one is technically not a polynomial because it has that exponent which is less than 0. But these are certainly polynomials. It doesn't matter if the coefficients are positive or negative. These all qualify as polynomials. All right, so the degree is a very simple idea. We mentioned this before, or sometimes it's called the order. And so the degree of a polynomial is simply the highest exponent in the function. Couldn't be any more straightforward. So therefore, let's look at these examples here. In this first case, because the x, and by the way, you can see now why it's so convenient to have the exponents listed from the highest to the lowest. It really makes our job simpler here because you can see very clearly here the degree is 4, here the degree is 7, and here the degree is 5. The coefficients are not relevant here. All that we're looking for is the highest exponent in that function. All right, so I think everybody gets the idea there. Then we have this concept of, you may remember this idea, the leading coefficient. Oh boy, what is that referring to? Well, this is the highest. It's the coefficient of the term containing the highest exponent. The leading, there's obviously one coefficient for each term, but the leading one, which often is important for our formulas, refers to the coefficient of the highest order term in the function. So for now, we'll just, remember that this is the case. We're not going to do anything specific with it just yet. Now, what's coming up next is a bit of a challenge. You might remember how to do this, or you might not. We'll go through this and we'll practice like crazy, but you can sometimes divide polynomials by each other, but it can be a bit of a mess. Okay, so that sort of is our signal that maybe it's time for a morning break here. We don't want to do something that complicated, or we don't want to start it and have to stop and then start all over again after the break. So I know you're all needing of some stimulation right now, caffeine, sugar, glucose, whatever you want. You're right at home there anyway. So why don't we fortify ourselves? Oh, yes, go ahead.
I had two things I was wondering about,
Okay.
just in general.
Yes.
Not having to do with what we've been like doing exactly, but are we
Uh-huh.
going to, like I did the chapter 3
Oh,
part
yes.
1
I'm glad you
problems?
reminded me. Yes. Yes, there is a chapter 3 problem set, which we haven't done yet. What I would like to do, let me go back and open it up for you. I'm glad you reminded me. Here it is. Oh, is that the right one? Yes, it is. Yes.
That's the one I did this week.
Oh, okay. I think there's a second one though. Yeah, I don't think I posted this one yet though. Because obviously that's only the first part of chapter 3. You know what? There do appear to be. Oh, yes, there are. You know what? I'll tell you what. I will. I don't know what happened here. It looks like I forgot to post it. Let's go back to Moodle for a second. I'm glad you reminded me because we got to practice. You know what I mean? It's got to be done because otherwise, it's fun to sit here and watch this and all, and you probably do understand it. It's just that you've got to make sure by doing practice problems. Let's see. Let's quickly jump in here. So it appears that oh no, there it is.
So should we do number 2 this week?
Yes, because we only just started this material. Let me just open it up and see. It's possible that we won't cover everything here today. We might. Let's just see. We've got the Vertex forum, of course, that we're now experts in. Okay, yeah, you know what? I think let's do this. Let's all agree that by this time next week, you will have done certainly the first half, chapter 3, practice problems number 1 is right here, and then do as much of this one as you can so that we can do it next week. All right. That's the only unfortunate thing about having like one meeting a week is because it's hard to get homeworks done. And then that way, we can make sure we're all on the same page. Oh, did we do that one last week? Oops.
Yeah,
Oh.
I thought so too.
Oh, all right. Well, then never mind. Then just do the second one. How about that?
And then my other question is, will there be like a set of like review practice problems that you'll assign for the midterm?
Yes, there will. It'll be
awesome.
It'll cover everything, believe me. So before you even think about having a test, besides the individual chapter practice problems, we'll have what's called a sample midterm, which is this
Awesome.
document full of problems from all the chapters. And then we'll get a chance to go through them all one more time. And then the test is going to be conducted on a take-home basis anyway, so that you'll have all your notes right in front of you. So, which should help a lot. But yes, we'll definitely have. I haven't posted it yet. I think I was afraid of scaring you, but no. It's yes, it's like all of these, but it's huge and it covers everything. And so that way you'll get one last chance to really practice like crazy with all this stuff. And then at some point we'll have the midterm, which, like I said, it'll be on a take-home basis. And so that way you can do it at home. You can take your time. All right, we got 2 more hands. Who wants to go first?
May I go first?
Okay, go ahead.
I was wondering if there's gonna be like an answer key for like the homework, just to go off to that to check if we had questions incorrect or correct.
Do you
Okay.
want that? I mean, usually what you normally do is I don't, because we're normally in the classroom and I see you all the. If you want to see the answers in advance, just send me an email and I'll send them to you.
Okay.
Okay.
Thank
If
you.
that helps you with it,
Mhm.
because this way, if you think you're getting stuck or something, you can look. But you have to resist the temptation to look at the answers before.
Oh no, usually when that happened, it's like I try like several times, and if I don't get it, then I just look at how.
I see what you're saying.
That's kind of how like Delta Math does it. So if you get a question wrong on Delta Math, it'll provide you an example of how to do a certain problem, and then you could go about taking notes and then actually internalizing what's being shown there, and then from there you could just use
Right.
what you.
So yeah, that's another point. Yeah, we can, as soon as I learn how to use it, I'll make sure that we've started using that Delta Lab before we have the actual test, so that you'll have more opportunities to practice. But it'll be optional. Have it's like this big system full of questions that have been written in advance that you can practice with, that might be helpful, but it won't be mandatory. But like it'll be available if you want to use it
Yeah,
on top of what we're doing.
it's just easier for me.
Yeah. All right. Well, just remind me, send me an email and I'll send it to you separately.
Okay. Are you checking your email like in the middle of class or?
No, I'm not.
Okay.
I,
Right.
I have other things to do, but
Yeah, of course.
unlike young people, I don't have the cell phone in my hands every second. You know what I'm saying? People send me
Yeah.
text messages and they wonder why I didn't get back to them within the 20 minutes. So like, well, I don't have the damn thing in my hand 24 hours a day. I'll see it eventually, So if you don't send me texts unless you need. I mean, if you send me a text, it'll actually take longer for me to see it most likely than an email, because I'm not in the habit of looking at them. I know where they are and I do get them occasionally, but I'm not like constantly checking them. Emails, I do look at it very regularly, but not so much text, because it's just, I don't know. I prefer the idea of having an email where I have a permanent record of it. And it's just, then I can type with my actual normal, keyboard, rather than fooling around with this thing. I find it very awkward to type on a phone, very awkward. And so I try to avoid text whenever possible. So if you're tempted to send me a text, think twice about it. Send me an email instead. Okay.
Sounds good. So I
Right.
could just forward you the email that I had sent previously to on the weekend.
Yes.
Okay, sounds good.
Because then I'll see it and it'll be all together in one nice, convenient location, and then I can do them in order. Whereas the text, well, it's just sort of a mishmash of everything here.
Mhm.
And you know what? It's just so awkward. I find that texts are very awkward. And so emails are definitely the way to go.
Okay.
All right, so let's save this division for when we get back. Now, once you start seeing it, you'll say, "Oh, I know how to do that." That's not a problem. But I don't want to start it and then have to stop and then pick it up again. We'll just do this fresh right after the break, and then after you see one or two of them, I think you'll realize that you still remember how to do this. Anyway, but we do have some formal note terms to introduce as well. But basically, I think you'll be pleasantly surprised at how well you remember how to do this. So anyway, so we'll stop right here. We'll come back in our usual 15 or 20 minutes, just enough to get some nourishment, refreshment. You cannot do math on an empty stomach, that's for sure. So let's do that, and then we'll dive into these divisions. We're going to look at a lot of functions or aspects of polynomials, including algebraic operations like this. All right, so let's knock it off for a bit, and I'll see you in a while. Oh, these crummy ads. Jesus. All right, here we go. I guess we're all back. Nice. So we're ready to do some long division with polynomials. Okay, so this is going to take you back a ways to the last time you've done this. So first of all, there's several terms that we need to remember here. It's kind of a nuisance to memorize a bunch of terms, but you've seen these before. Anyway, formally, we define the dividend, which is what results from dividing a polynomial by another polynomial, and we have a quotient, we have a divisor, and we have a remainder. So when you see the numerical examples, this will seem a lot more straightforward. But yes, unfortunately, there's all these terms we have to remember now. But you've seen them all before. So don't worry. When you see this, you'll say, wow, how easy is it possible to get? All right, so as soon as you're ready, I'm going to show you the first example. Actually, I'm going to write it out on a separate slide here. And then, hold on one second. All right, oh, what happened? Here we go. Yeah, so based on that, here's what we're going to do. Now, when were a little kid and you were learning how to do division, you were using a technique very similar to what we're doing here. So let's say we decide to take this function f of x is 2x cubed minus 3x squared plus 4x plus 5 and divide by x plus 2. Okay, now here's one way we can do this. So we're going to take the x plus 2. I'm going to write out. Oh, is it starting to look familiar? Yes, it is. 2x cubed minus 3x squared plus 4x plus 5. Now, what are we trying to do here? We've got to come up with a value, probably some function of x, which when multiplied by x plus 2 will help us eliminate 2x cubed. So let's try 2x squared. So I'll try to hide this over on the side here. If you multiply this expression by 2x squared, you'll have 2x cubed plus 4x squared. So I'm going to write that down here. 2x cubed plus 4x squared. Now what am I going to do? Oh, hold on one second. Let me just, I've like no room here. Okay, I'm going to subtract this. But be aware that I'm subtracting both terms. In other words, this becomes negative 2x cubed, and this becomes negative 4x squared. Okay, so in other words, by putting a negative out here, you can think of this as a negative, and this becomes a negative as well. These drop out. And here I end up with minus 7x squared. Now I'd like to get rid of that negative 7x squared. So I need some number or some value, which when multiplied by this expression, gives me negative 7x squared. So let's try negative 7x, I mean. Why did I pick negative 7x? Because if you multiply minus 7x times x plus 2, you'll have minus 7x squared. Oh, I almost forgot one detail. When you bring this down, this one comes with it. Okay, in other words, this difference is negative 7x squared, but then we need to bring down this term so that we have two terms. So when I multiply negative 7x times this, I get negative 7x squared minus 14x, which comes over here. And again, I want to subtract them both, which means this becomes a positive, this becomes a positive, these drop out, and I have 18x. Bring this down. And then I can try 18. That gives me 18x plus 36. Subtract everything, minus 31. Now that, I'm done now. I can't go any further. So what this means then is the following. I've got a remainder of minus 31 over x plus 2. Okay, so in other words, I've got 2x squared minus 7x plus 18, but then I have this little remainder down here. So the final result of this division is this. All right, let me just show you, then I'll come back to this. So you've got the expression I had here, plus this is my remainder. Okay, so in other words, this polynomial does not evenly divide into this one. So therefore we have a remainder. All right, so let's go back and revisit. How did we do this? Well, now remember, like I said, you've seen this technique before, but maybe not with polynomials. The first time you were ever introduced to division as a child, you did something just like this, or you probably did. Maybe you don't remember anymore, but something like this is what you would have been taught to do. And so it's the same idea, except that these are now polynomials. All right. Well, that was, now, as far as the notation goes, let's go back to, yeah, so the dividend is this expression. The whole result is the dividend. And that's equal to the divisor times the quotient. This is actually the quotient. And this is the divisor. So in other words, if I multiply the right-hand side here by x plus 2, I'll just end up with the original function. All right, so you know what? Why don't we do, oops, I made a mistake here when I drew this thing. Hold on one second. This is not the dividend over here, sorry. The dividend is the original function. My mistake, sorry. This is the dividend. The dividend over the divisor gives me a quotient plus a remainder. That's the way to think about it. I think this is easier than what we had before. The dividend is the original function. We divide that by some divisor equals a quotient plus a remainder, if any. The remainder could be 0. Now, in the book, they've decided to associate each of these with a different functional name. The dividend will be from now on known as f of x. The divisor will be known as d of x. The quotient will be known as q of x. And the remainder will be known as r of x. All right, so when you see those terms, you'll say, oh, I know what they're talking about. Now, of course, you notice they almost ran into trouble here. There's 2 d's, but they've decided, yeah, the dividend is the original function, so they're calling it f of x. The rest of these, the letter is just the same as the first letter of that word. Now there's some restrictions here. Well, first of all, obviously d of x cannot be 0. We can't have division by 0. As we already know, we've seen that cool video which explained that to us in great detail, because there's no multiplicative inverse for 0. The degree of x, actually, let me write this on another page because it's starting to take up a lot of space. Hold on, maybe I can fit it in down here. The degree of x is less than or equal to the degree of f of x. Of course. And the other restriction we have here is on the remainder. R of x can either be 0 or the degree is less than the degree of f of x. Okay, so those are the constraints, but I mean, we don't have to memorize that. It's just, it should be pretty straightforward to see that. Now, you know what, I'll tell you what, why don't we do something like this? I'm gonna make another example, which is not so messy. All right, hold on one second. All right, let's try another one, just so you can get some more practice with this. Let's divide x squared plus 2x minus 8 by, let's say, x plus 4, just to get a better feel for how this works. Okay, so here's how you'd set it up. We have x plus 4 dividing into x squared plus 2x minus 8. So we'll start with x. Now, if I multiply x by x plus 4, I'll do that over here, equals x squared plus 4x. I'll put that down here. And remember, what I'm trying to do is subtract. Ideally, both of these would drop out, but that's not going to happen here, is it? No. This becomes negative. This becomes negative. So I actually wind up with these canceling out. I have minus 2x here. And then I also have minus 8. This always comes down. Now, what I'm going to do is multiply this by negative 2, because negative 2 times x plus 4 is minus 2x minus 8. If I subtract that, both of these become positives, and I end up with 0. So what that proves is that x squared plus 2x minus 8 over x plus 4 equals x minus 2. So here we have a dividend. The original function is the dividend. D of x is the divisor. Q of x is the quotient. And in this case, R of x is 0. There's no remainder. Okay, so that means we're done. We've divided successfully x squared plus 2x minus 8 by x plus 4 to come up with this result. Okay, so that was more straightforward, I think. The one we had a minute ago was a little bit messy, so maybe we should not start with messy ones. Let's see if I can come up with another one. Hold on one second while I plan one out. All right, here we go. Let's try another one. We're going to divide the function x cubed plus 3x squared minus 6x minus 8 by the divisor, which is x plus 1. All right, so let's do it the way we've been setting it up to this point. X plus 1 divides into x cubed plus 3x squared minus 6x minus 8. So we're going to start with an x squared term because we want to get rid of this x cubed. Let's try x squared. Why x squared? Because if you multiply x squared by this, you'll get x cubed plus x squared, which I will now proceed to subtract. This becomes negative, this becomes negative, and now I've got 2x squared. Bring this down. Now I've got to figure out a way to get rid of that 2x squared. Why don't I try plus 2x? Okay, because 2x times x plus 1 is 2x squared plus 2x. Perfect. So I'll have 2x squared plus 2x, subtract everything, which means this is now negative, this is now negative. These drop out. I end up with minus 8x. Bring this down. Now I want to get rid of this minus 8x, so let me try minus 8. Minus 8 times x plus 1 is minus 8x minus 8. Perfect. And that means that once again, we end up with no remainder. Okay, so the quotient is what we have up here, and the remainder, r of x, is what we have down here. Whew, that was exhausting, wasn't it? All right, are we getting more comfortable with this approach?
Somewhat. It's still a bit annoying.
Still a bit much.
to
All
look
right, well,
at. Yeah.
that means we need another one. All right, let's try another one. All right, first I have to make it up. Hold on, this is going to take a second.
So like the goal, so every time you put something above the dividing thing, you multiply it by.
Yes, exactly. So in other words, what I'm doing as I move along is what, like x squared gets multiplied by this to reduce what's coming up down here. Then I multiply by 2x to come up with that, what I put down here in parentheses. So in other words, what it is that I want to subtract is coming from the product of this term that I put on top and the original divisor.
Okay, so divisor times thing on top.
Divisor times the thing on top gives us the plus the remainder, if there is any, will give us back the original function. In fact, why don't we prove that one right now? Because maybe you're skeptical. So watch this. If I now, by the way, I'm going to show you a technique that you might or might not know. My quotient is, I'll repeat it here, x squared plus 2x minus 8. And my divisor was x plus 1. Let's multiply these together. Now watch this. If you've never seen this technique before, well, I like it. What I'm going to do, let me just give myself a little more space here. I'm going to multiply these two polynomials. Now I'm not using FOIL, if you notice, because this expression up here is not a binary expression or binomial. Watch how easy this is. I'm going to multiply this 1 by each of the terms on top. And then I'm going to do the same thing with the x. Minus 8x, 2x squared, x cubed. And so I've got x cubed. These are both positives. This is minus 6x minus 8. And that, of course, is the original function. So we just proved that we've done this correctly. So we're even more satisfied because we can see that we must have done this correctly, because the product of D and Q gives us back the original function. Now, if it didn't, if there was a remainder, instead you would have had this dx qx plus rx would have given us f of x. In fact, now maybe that original expression, remember way back here, we saw this, we said, oh, what is going on here? So f of x equals d of x, q of x, plus r of x. Now all of a sudden it starts to make a little sense, doesn't it? Why, yes, it does. All right, let's see. I'm still working on this new example for you. All right, let's give this one a shot. F of x equals x cubed plus x squared minus 5x plus 28. And d of x is x plus 4. All right, let's do it. By the way, does this ring any bells? Does it look like something you've done before? Maybe not. Maybe it's been too long. All right. So the first thing we want to do is, as we go from left to right, we want to eliminate these terms. So in order to get rid of this x cubed, we'll have x squared here, because I'll hide it up here, x squared times the divisor is x cubed plus 4x squared. All right, so we'll put that here. Then we subtract the whole thing. So that means this becomes negative. This is now negative. And I've got 3x squared. Bring this down. Now what do? I want to get rid of this 3x squared. Let's try 3x. Why? Because 3x times x plus 4 is 3x squared plus 12x, which I'll put right here, 3x squared plus 12x. Again, I have to subtract, so I end up with minus 7x plus 28. How do I get rid of that minus 7x? Let's put a minus 7 here, because minus 7 times x plus 4 is minus 7x. Hold on, I'm running out of space here. If I multiply minus 7 by x plus 4, I end up with minus 7x minus 28. And when I subtract that, these both become positives. And I've got a remainder of 0. Woohoo! Okay. So in other words, the quotient, we know what f of x is, the original function, the dividend. This is my divisor. The quotient is what we're finding on top here. And in this case, once again, we got lucky and we have a remainder of 0. All right, do we need another one? Sure, why not? All right, first let me plan one out for you. All right, here we go. We're going to divide. So remember, f of x, the original function, let's go back to the beginning when we had all this scary terminology, is the dividend. This time we'll try x cubed minus x squared plus 4x. And the divisor, d of x, will be x plus 1. So your job is to look for the quotient and any remainder, if there is one. So we set it up as x plus 1 divides into, by the way, I almost forgot to mention this. If any of the terms are missing, let's say that there's no x squared here. And this is, I should have made an example like this, but you would put 0x squared here just as a placeholder. If you leave it out, you're going to get confused. So if that happens, let's say there's no x squared here, you do need to put it in here as a 0 in order to act as a placeholder. Otherwise, this technique will not work correctly. Okay, so we haven't seen that yet, but then it just suddenly dawned on me that it could happen. So I'll tell you what, just because we've already done so many of these, why don't you take a minute and see what you can come up with here. And if you get stuck, well, we'll go through it together. All right, why don't you take a crack at this one and see what you can get. And I'll give you a hint, there's no remainder in this one. All right, so I'll give you some hints. You need to get rid of this x cubed. Let's try x squared. Okay, and x, oh, somebody's got it. Okay, x squared minus 2x plus 6, that's it. No remainder, perfect. It is x squared minus 2x plus 6. Let's see why. Yes. All right. So x squared, if I multiply this by the x plus 1, I have x cubed plus x squared. Now you subtract, which means you're changing the signs inside here. These drop out, which is what we were aiming for, minus 2x squared, and then you have to bring down the next term. Now we need to get rid of this minus 2x squared, so let's try minus 2x. Because now, if I multiply that by the divisor, I get minus 2x squared minus 2x. And when I subtract, I have 6x plus 6, and the way to get rid of a 6x is to put a 6 here. And they just nicely drop out, and I'm left with 0. So this is my quotient, and this is my remainder. It's always nice when it works out evenly, isn't it? Yes, it is. So you're probably wondering, why are we doing this? Well, because it helps us find solutions for higher order polynomials. That's really one of the main motivations for doing this. Like, for example, what if you saw that this function, x cubed, in fact, you know, why don't we go look at Symbolab for a second? Let's bring this over there. And you know, it looks like it's going to be fairly involved. Y equals x cubed minus x squared plus 4x plus 6. Yeah, that's it. So we're going to graph this. And now this is one of those cases where there's only one solution. So what you can do now is, like, you could set this equal to 0 and try to solve for it, but it's usually easier if you can break it up into smaller pieces and set them equal to 0 to find the solutions for this equation. So one of the reasons why you might want to do some division like this is to take a large polynomial and break it up into simpler pieces so that you can find the solutions. All right, here's one that you should be able to handle now. I'm going to show it to you, and I want you to do it for me. Now, this one, unfortunately, I think has a remainder, but why don't you try this and see what you come up with? So this is, there's the setup. With a fancy division sign instead of the flat one I had. It's fancy division time. Oh, somebody's got it. Let's see what you have. Is it 5x minus 2? Is it? I actually don't remember. Oh, well, guess what? I forgot. I thought this one had a remainder. It doesn't. You're right. It's 5x minus 2. Now, here I've written it out by hand. just because it was quicker than trying to type it up. But you can see these are the steps that you would have followed. All right. So you start out with the 5x. Why do you need 5x? To get rid of this 5x squared. You subtract these off. This becomes negative. This becomes negative. So you have negative 2x minus 2. This one has to come down. And to get rid of a negative 2x, let's multiply this by minus 2. And so you got minus 2x minus 2. This time there's no remainder. What do you know? It's always a nice day when there's no remainder. Okay, so this is your f of x. This is your d of x. This is your q of x. This is your r of x. Yep, it always feels very pleasing when there's no remainder. Oh, there's one more. Oh, yeah, bad news. This next one is not only looking more difficult, but it has a pretty nasty little remainder. But you know what? By now, I think we're really and truly ready for it. All right. If you can't, I mean, if not, that's okay. This one's going to take a little longer because the divisor is a quadratic, so a quadratic function. So I'll tell you what. I'll give you a few minutes to do this one too. If you can do this one, you're set. We can go on to a different topic because this one is pretty challenging. All right, so you ready? Is everyone up for the challenge? Okay. If we're in the classroom, I'd be hearing a lot of cheering, but we're not there. So I'll just give it to you. So this is what we want to do. And you can see this one will be a little more time consuming because you do have a quadratic function for your divisor. All right, so once you take a few minutes and see what you get, and I have to tell you that sadly enough, this one has a remainder.
Plant that thing in there. So pat it down. You're gonna want to water it, and we are good to go. Okay, everybody. Snowdrops. Put the soil line. Snowdrops you really like. Yeah, that's a pretty one. Good. Dig that baby up. Go shake some of the soil off it. Good job. Divide it. Yep.
Oh my God, somebody's already got it. Oh, okay. So we've got 4x minus 9, and the remainder is 12x plus 16 over all of that. That is absolutely correct. So we've got some people in here who are fast. You know it. Well, you know what? Let's see. I've got, yeah, here it is. Let me just show you. This is the thing all done step by step. So we didn't get very far. You've only got 4x minus 9. And when we're done, we just have this. And you can tell you're done. You can't go any further because the order of what's left is lower than the order of the dividend. And that means you have to stop right there. Okay, remember the dividend itself right here, the divisor, the remainder has to have a lower order than the divisor, or else it'll have to be 0. So that's how you know to stop. This is a linear function. This is a quadratic function. So that means you're done. So the final answer is that when you make this division, you've actually got f of x equals 4x minus 9 plus 12x plus 16 all over this expression, x squared plus 3x plus 2. Now, if you want to spend the time, you can algebraically prove this. You would turn this 4x minus 9, you'd give it a common denominator equal to this one, and you can go through all the steps. We're not going to do that here. As long as you did the division correctly, that's all we need to know. All right, now what we're going to do here is we're going to quickly look at techniques for finding the solutions of higher order polynomials. We already know that we have that wonderful quadratic formula for quadratic equations, and that's fantastic. But for the higher order polynomials, we don't typically have a nice formula like that. So there are other techniques that we have to lean on when we're dealing with higher order polynomials. Now, some of these are very, very time consuming, so we're only going to look at a few special cases. So we just want to be aware of the fact that, you know, solving for polynomials is not just restricted to quadratics. We can use it, there are techniques available for basically any order polynomial you could imagine. All right, so we'll start that as soon as everyone's done right here. Just make sure you see what happened. Okay, so remember, when you apply this negative sign here, this becomes negative. These drop out, this becomes negative, and this becomes negative. That's why you end up with negative 9x squared here and minus 15x. And of course, this comes down. Then we did minus 9, which gave us all of this. And by subtracting, this becomes positive, positive, and positive. These drop out. We have 12x, and we have 16. All right. All right. All right, so I guess we're basically ready to start. So there's 3 different techniques that we want to briefly consider. There's many others. Okay, once we get, like I said, above from cubic and up, you know, the different solution techniques, there can be many of them, depending on the signs of the coefficients in our polynomials and other considerations. So we may have to only focus our attention on special cases. Now, you know, interestingly enough, what's funny about some of these cases is that you may actually be able to solve these directly with Symbolab. It has some capability, as far as I know, of solving for these equations. So what we may want to do is, when we're done, double check our results with the Symbolab. And, you know, there's other techniques, software products as well out there. For example, if anybody here is actually majoring in math, there's something out there you might be interested in. It's this thing called Mathematica, which basically, it solves a lot of these types of equations. It's very, very powerful. And not only that, but, you know, a lot of colleges do have software available for their students. I'm not sure, though, if Purchase offers this one. You know, let's find out what they have. Every college has Microsoft Office. Let's find out. They have, oh my God, I am so impressed. They are offering here, right here on this very page, you can go there and say, please give me a copy of Mathematica. SPSS is a statistical package, which you might use in a social sciences course like biology or psychology, if they're doing statistical analysis in a class like that. Mathematica is just straight ahead math. Some of these others, I think, isn't Final Cut? Don't hear ever use that? Isn't that the one that lets you make videos? I think that's an Adobe product. Let's find out. I have to know. Yeah, it's a video editor. What's going on here? Well, I guess they're just, you know what, obviously what this means is that like the company that makes Mathematica, here's the logic behind this free software. It only lasts while you're still in school. So what they're hoping is that you will get used to their software, and when you graduate, you'll buy it. I mean, that's really what this is all about. I mean, yes, they're trying to be nice and all, and that's wonderful. But ultimately, what they're hoping you'll do is learn how to use their software, and you will decide to buy it for real when you graduate. And that's fine. In the meantime, let them give it to you. So is anyone here actually majoring in math? I mean, I know I can look it up on the roster, but I was just wondering. No. Am I seeing no yeses? I mean, oh no. Well, that's okay. You have other things to do, but let's just say you decide one day, I kind of like math. Maybe I could at least be a minor, okay, to go along with my major. That might be fun. And then you might get some real benefit from having a package like this. But it's just basically like a really hardcore version of Symbolab when you come right down to it. But yes, if you're deadly serious about math, this is the kind of software you really should have, because it can do so many different things for you. And it's used in the real world by actual mathematicians. This is serious stuff. Man, see, then look, they're telling you, wow, they're really zooming it up there, aren't they? All right, I just thought I'd throw that out there just as an idea. And yes, as a hint, you can actually minor in math if you suddenly realize that, you know what, this is pretty good stuff. I wish I could have more of it. Okay. Yes. Anyway, so let's get back to it. So we're going to see three different ways of approaching the solutions of a polynomial. And they are called, as you can see, the remainder theorem, the factor theorem, and the rational zero theorem. All right, so let's write these down for a second and let's take a peek at what they look like. And some of these are very straightforward and some of these are not. Okay, some of them can be a real nightmare. All right, why don't we begin with the remainder theorem? Now, the remainder theorem only applies to the special case where a polynomial is divided by x minus k, where k is some constant. Now, what it's telling us is it's not really giving us the solution. Actually, it's giving us the remainder. It just so happens that if that's the case, then your remainder is f of k. I'm not sure realistically how much that helps, but it is an interesting result. Okay, so I'll tell you what, since we're so good at this now, why don't we try the next case? Do the division and see what you come up with for your remainder. All right, so once you do this division, and when you're done, what we're going to do is confirm that the remainder is in fact, oh, I don't want to show you the answer. Well, first just do the division and then we'll check it out from there. Okay, we have an answer. It is indeed 24. Yes, it is. All right, let's see why. All right, so I went through the steps. And okay, we begin with 2x because we need to get rid of this 2x squared. So we have 2x squared minus 8x. So this becomes negative, this becomes positive. These drop out. We end up with 4x. We bring down the 8. Now we need to get rid of 4x. We'll multiply by 4. And we'll have 4x minus 16. So here's our remainder, right? So once again, this is the divisor. This was the dividend. This is the quotient. And this is the remainder. Now, because the divisor is f of x, it's written as f of x minus k, right? Oh, hold on. No, just x minus k. Okay. That implies that k is 4. And they're telling us that the remainder, r of x, should be f of 4. Well, let's prove it. This is the original function up here. So f of 4 would be 2 times 4 squared minus 4 times 4 plus 8. 32 minus 16 plus 8. Well, what do you know? It works. So it's an interesting result. But it's not giving us the actual quotient, which is really what we're ultimately after. But it does give us a quick way of determining what the remainder is. So that's one technique we can use now here we happen to have a quadratic function to start out with, but this could apply to any order we want. It could be a cubic, it could be anything higher than that. We'll still get the same result. So that could potentially come in handy. So, all right, now, the next one is a little bit more involved. It shows us, well, actually, before we do that, let me just take a step back and review something really fast with you. And that would be factoring quadratics. Let me introduce, just in case you've started to forget how this works. Suppose you had something like this. I have to quickly plan this out for you. Suppose I have x squared plus 2x minus 8. What are the factors of f of x? Well, these are binomial expressions actually, I should say 2 binomial expressions whose product equals f of x. Now, let me just show you a fairly formal derivation of this. This will only take a minute. Suppose we have x plus m, x plus n, where m and n are real numbers. And so by using our old friend FOIL, which nobody forgets about FOIL, the quadratic formula and FOIL, nobody forgets. F, or first, is here. That's x squared. Here's n times x. That's O, or outer. I, or inner, is mx. And then last are these two. So this product is x squared plus nx plus mx plus mn, or more simply, n. Okay. Actually, just to be consistent, let me do this. Not that it matters. Okay, just so that, because m comes first alphabetically. Now, so what this is telling me is that if I have a quadratic expression like this one, I can break it up into these two factors. Now, the main reason why we might be interested in factors is because we can use these to help us solve a quadratic equation. So imagine we had the equation, the one I just showed you right here, x squared plus 2x minus 8. Why don't we do two things here? Let's find the factors and the solutions. So, all right, so f of x, once again, is x squared plus 2x minus 8. So to find the factors, we need two integers whose product is -8 and whose sum is 2. Why? Because this is your mn and this is m plus n from before. All right, so in other words, you see the coefficient of x is the sum, and the coefficient of, or the constant rather, is m times n. Now, what integers are we looking for? Well, let's see what we can do. We could try -1 and 8. Their product is -8. We could try 1 and -8. We could try -2 and 4. And we could try 2 and -4. In all cases, the product equals -8. In only one case, though, is the sum equal to 2, and that's right here. Oh, go ahead. Yes.
Yeah, so for the factor theorem, we could either use things like the AM method or cutting the polynomial in half and then setting it equal to 0.
Oh, yes. You mean completing the square? Is that
Yes, yeah.
Yes. Oh, absolutely. Whatever techniques you've learned along the way, you can use those if you feel more
Right.
comfortable. Yeah, they're never going to say to you, you must use a certain technique to find the solution. There's usually multiple ways of going about anything in math. And so you're going to pick the one that makes the most sense, either because it makes sense to you or because it's just more straightforward. So it's like anything else. There's always a million ways of getting where you want to go. When you get in your car and your GPS, says, oh, go this way, and you disagree with it, and you start to go the other way, it corrects itself because, it's saying, oh, you want to go that way, huh? And then that's how it works,
Yeah.
It's like it knows that you're the boss. It says, oh, you want to go down that little crappy side street? No problem. I'll show you how to get there. Because it doesn't understand, like if you want to go the scenic route or something, it doesn't understand that you just want to avoid traffic. It's just trying to get you there with the least number of miles. And I don't think it's sophisticated enough just yet to do anything other than just minimize the number of miles. So you've got to sort of help it a little. And so here's the same thing. You've got a bunch of techniques to choose from, and you pick the scenic route, let's say, whatever works for you. anyway, so what this is telling me then is that the factors of this polynomial, or actually in this case quadratic equation, are x plus 4, or actually let's write it like this, x minus 2 and x plus 4 are the factors. Okay, so let's move this on to a new slide because we're running desperately short on space here. All right, let's, yes, we're getting really low on time, space here. So once again, this tells me that x squared plus 2x minus 8 could be written as x minus 2, x plus 4. These are the factors. And you can prove it with FOIL if you want to. F would be x squared. O would be 4x. I would be these two minus 2x. And O, last rather, would be these. Okay, so those are the factors. Now, the solutions, though, mean that you're setting each of these equal to 0. And so that means that the solutions, though, are these two values. In other words, 2, 0 and negative 4, 0. And that's because if this equals 0, then so do these. And if this product equals 0, then each term individually equals 0. And then we end up with this. So these are the actual factors, x minus 2 and x plus 4. The word factor indicates that these are binomial expressions, meaning there's two terms within the parentheses. Now that's great for quadratic equations, but it's more general than this. I mean, we need to know what to do with higher order polynomials as well, because you never know what we might run into. Imagine yourself sitting down at your job one day as a professional mathematician, and the boss says, well, you know what we need? We needed some solutions to this polynomial. You say, no problem, boss. And you sit down and work on it, and before you know it, you've got a solution. So the factor theorem says this: K is a solution of f of x. And it's kind of a strange idea, but we're saying that K is a solution. Now remember, solution means that's the value of x, where this crosses the horizontal axis, or where y equals 0. So K is one of the solutions of this function if, in this case, f of x minus k, wow, this is a complicated one, isn't it, is a factor of f of x. So in other words, once you've calculated the factors, in fact, you know what, well, all right, let's just see this, how it applies to this next case. We've got a polynomial. It's actually a cubic equation because the highest order term is x cubed. What comes after this, I think, is quartic. And then after that, I don't know. In fact, why don't we go to Google for a second? This might be fun. Oh, here we go. Quartic, oh, here we go. Look at this. We have quartic, quintic, sextic, heptic, and octic before they stop having names. No, according to this one, it would be nonic and then decic and so on with Latin numerals. Wikipedia explains this to us. Oh my God, look at this list. Cubic, quartic, quintic, sextic, heptic. Jesus, they even have pictures of what these things look like. Isn't this amazing? For the other issues that maybe Wikipedia has, it certainly does a good job with math and statistics. That's been my experience with it. Man, some of these functions are really bizarre. But the reality is you're not likely to run into many of these in practice. In the real world, you're probably not going to go much beyond cubic. But it's fun to know where these names are coming from. And they're coming from the Latin. Of course, everything here is Latin. In fact, while we're talking about this, there we go. Who knew this? I didn't know. So you can see, the word unit actually comes from this then. Unit means one, duo for two, tres for three, quatuor, I don't really even know how to pronounce these properly, quinque, oh man, that's interesting, septem, octo. Anyone here ever study Latin in high school? No. Yeah, even when I was in high school, they started getting rid of it. They pretty much switched over permanently to European language. Oh, you did? Was it a nightmare? The thing is, sometimes certain types of knowledge, though, they might have been a pain to learn them, but man, they might come in handy. I'll tell you what, if you ever find yourself on Jeopardy, it'll come in very, very handy because half the clues have something to do with Latin, if you've ever noticed that. Is it help with the SAT? I bet it did. Sure, especially the English part. Sure, absolutely. But yeah, there you go. And of course, the Roman numerals. Wow, it's all good. There's all knowledge is good when you come right down to it, but especially math. Woohoo! All right, so here, more practice. Why don't you try dividing x plus 2 into this cubic equation? We could always use more practice. Let's see what you come up with. Okay, x squared minus 8x plus 15. I believe that is correct. Yes, it is. 8x squared, sorry, x squared minus 8x plus 15. Perfect. This time the remainder is 0. But what we'd like to do is factor it now and test out this theorem, this wild theorem. By the way, let's make sure you got this part right. First, we needed to get rid of this x cubed. So we multiply by, we have x squared here. So we have x cubed plus 2x squared. Subtract, we have negative 8x squared. Bring this down. We now need to get rid of this negative 8x squared. So we'll try negative 8x. And that will give us negative 8x squared minus 16. These become positives. These drop out. 15x plus 30 comes down. Oh, yeah, that worked out beautifully, didn't it? Now, factoring this expression, if we want to factor it, we need to make sure we find two integers whose product is 15 and whose sum is negative 8. And so that means, and so we'll speed this up just a little bit because we're running out of time. Minus 5 and minus 3 will satisfy these requirements. So we can say that x minus 5 and x minus 3 are the factors of this expression, which further implies, if we need to know this, x minus 5 equals 0, x equals 5 is one of the solutions, and then x minus 3 equals 0, x equals 3. These are the solutions. Okay, and actually, why don't, just for the fun of it, let's go back to our friend Symbolab and see what this thing looks like. Where did it go? God, I've got so much stuff open here. Here we go. So we need x squared minus 8x plus 15. And there it is. So yes, it's got the two solutions, 5, 0, 3, 0. So those are the solutions 3 and 5. And you can see it also has a vertex right here. But what we wanted to do is prove that because, oh, wait a minute. Oh, yeah, no, this is a result from our division. But, okay, I see what happened here. They didn't want these factors. Although you can write this now as x plus 2 times x minus 3 and x minus 5. But I don't know if we really need to do that. Let's see. Oh no, that's where it was going. Okay, we just jumped ahead a little bit. So yeah, there it is. So yeah, oh, that's interesting. -2 is also a solution. It didn't show up. Oh, you know why? I think I graphed the wrong thing. That's why. I was supposed to graph the original function. No wonder. Y equals x cubed. That's why it didn't show up properly. Minus 6x squared. Oops. 6x squared minus x plus 30. And then we'll see, since this is a cubic, it does have three solutions. We found the factors are right, but so you can see it crosses the axis at -2, 0, 3, 0, and 5, 0. So this is the one that we forgot about. And so in other words, what they're saying here is that all you have to do is take the factors. Now, we did the division, but we still had the quadratic function, which can itself be broken down into two more factors. So this is what we were looking for right here. And then this is just like what we did with our quadratic cases. We just set them all equal to 0 individually. And these are the three solutions. What's different now, though, is that we have a cubic equation, which means in order to use the factoring technique we had before, we needed to find some way to split it up into something smaller. In other words, by doing this division, we're able to reduce this to a quadratic equation or quadratic function, and then it's much easier to find all the factors. In other words, if you had started with that cubic equation, it would have been difficult to find all three of these. But by using division to simplify, that became much simpler to find all these factors, and then, of course, the corresponding solutions. Wow. And then, of course, you probably should double check them. All right. Now, the third and final, oh, here we go. No, it's not the same K. Sorry, it's just some arbitrary constant. Yeah, we have to be careful. In the vertex case, the K specifically refers to the Y coordinate of the vertex. Here, K can be just any constant. So yes, I agree with you. That can get confusing. So we just have to be careful. Here, it's literally just any constant. But in the case of the vertex, it had a more specific meaning. So here, it's just literally any constant. But anyway, the third and final technique is the so-called rational zero theorem. And basically, we're going to find out that we can find the solutions basically through division. I mean, really, that's what this is all about. Rational meaning ratio. So this one is a little bit messier. So I think maybe we should sort of save this one for next week. But there's some interesting applications here, though. From physics. Remember physics? Yes. Oh, yes, you remember this stuff. Look at this question. A tank fills with water at the rate of 10 gallons per minute. Sugar is poured into the tank at a rate of 1 pound per minute. Initially, we have 100 gallons of water and 5 pounds of sugar. And we want to know, after 12 minutes, has the concentration of sugar increased? So you remember doing this stuff, but we're going to show you a formal way of doing these types of problems using these rational functions, as they're called. Okay, so but we're going to have to save this. And then, of course, we always want to ask questions about the domain and the range of anything that we do. And then we'll wrap up this section with another discussion about inverses, where this time we're going to get radicals involved. And then we'll be ready for 4, for God's sake. It's about time. 4 is a very exciting chapter because it gets involved with exponential and logarithmic functions, which are something that's very heavily used in the real world. You see this everywhere. In fact, I have an application in here somewhere that involves interest rates. So it's always kind of nice to bring, and how quickly the value of a painting is growing, that kind of thing. So it's always fun to have or how fast the deer population is growing. There's a lot of fun. Ooh, man, there's some fun applications in here. So anyway, but sadly, we'll have to save all that for next week. In the meantime, what I want you to do is work on the chapter 3 problem set number 2. We've already done the first one, apparently. Now it's time for the second one. All right, so that's all you have to do. Make sure you go through the notes and understand what we've done, but also work on the second problem set. And I think, let's just look at it. Oh, no, I don't want you to see the answers. I think that we have covered enough, almost enough. If not, we'll wrap it up next week and we'll do it then. Okay. All right, so yeah, it's pretty late. Why don't we knock it off? So there's your math for the week. Hopefully you feel stimulated as a result, and I'll see you all next Wednesday.
Thank you for your time, Professor.
See you later.
I'll send you an email regarding Delta Math during the weekend.
All right, good. All right, see you later.